Okay, good morning everyone to the second day of our conference. It's my great pleasure to announce our first speaker of the morning session, Bailok Hu, who is here from the University of Maryland. Bailok is an expert on so many things, quantum gravity among them, quantum field theory, on curved spacetimes, in the early universe, in non-equilibrium situations. He has thought a lot about quantum foundations too. And in addition, we are very grateful because he gave up one of his ironclad principles, which is not to waste his precious summer by going to conferences. So we are extra grateful that he's here today, and we'll be talking about theoretical basis for low energy quantum gravity and quantum information phenomenon. So welcome and thank you, Bailok.
Thank you so much, Renata, for your kind introduction. I want to thank the organizers, Frank, Renata, Beatrice, for such a wonderful conference. It's one of the best I've attended, really. For one, there's plenty of opportunity for young people to present their work, and I think that's a very great thing to do. And even tending to details like missing power supply, otherwise you would see a much earlier version of this. So let me try to capture the essence of a few things. How is the sound from, because I speak with a really weak voice, my students always complain about it, but you can adjust it whenever, yeah. All right, so I've divided it into 3 parts. The first part is pure philosophy. You wouldn't see any equation in it. And basically, I'm just asking one question, that I've been asking for the last maybe 30 years or more. And because now quantum gravity has developed so much, and in fact, I'm trying to take this opportunity to find out the different answers to my one question that I'll pose to you in the first part. And the second part, I'll just go through gravitational decoherence and gravitational as 2 sample issues wherein one could, in principle, carry out tabletop experiments. And in fact, that's what stirred up a lot of interest and attention towards tabletop, in quote, experiments for quantum gravity. One has to be really careful about what one means in quantum gravity there. And then the third part, if I have enough time, I'll also show you another topic which has to do with graviton noise. In some sense, people know that it's very difficult to directly detect gravitons. And they say, well, what about whatever noise that it carries? And we show it's still kind of minuscule, the effect, but at least those are a few avenues representing low energy quest for the quantum nature of gravity. So, disclaimer. First of all, this talk is not about quantum experiments in gravity or analog gravity. There are lots of nice reviews, as you can see. And I'm not an experimentalist, nor am I a versatile enough theorist capable of doing quality experiments. There are people who are capable of doing that. And this slide was prepared before I knew that Marcus Aspermeyer can't come. I was hoping that he would fill in all the gaps about experiments, and you can ask him any question about it. Well, you can do so for the next speaker, of course. And most importantly, this is not a review. Again, there are many excellent reviews. I read the one that was mentioned, in fact, discussed very nicely by Bianca in the opening talk here. I would invite you to take a look at it because the perspective has changed so much compared to, let's say, 30 years ago. And I also want to remind you that so-called tabletop could be as big, the table could be as big as LIGO Virgo, 400 kilometers, or even stretching to deep space like DSQL. That's the newest NASA initiative, preparing to put men on Mars through manned station, person station around the moon, that sort of thing. And so, in a way, never mind about whether the tabletop specific experiments that you've read about it is about quantum gravity at the Planck scale. They are not. I just want to tell you, they're not. At best, it's perturbative. And in fact, even not perturbative in the sense that if you only look at Newtonian force, it's pure gauge. You cannot talk about the quantum or the classical nature because it's slave to the masses. In the case of E&M, is the Coulomb force being the pure gauge. You really need to get to the level of photons to talk about the quantum nature of it. So, what I was referring to is that it's worth paying attention to some of these large-scale experiments, which I would also consider that as tabletop, all right? So you might wonder at this point, what am I doing here, right? It's not a review, it's not about experiment. So instead, I'd like to discuss some fundamental theoretical issues of low energy and emphatically perturbative quantum gravity when quantum information issues like decoherence and entanglement are invoked in any proposed tabletop experiment, okay? So it's mainly the theoretical basis that I'm focusing on. And so I mentioned there are reviews, and there's one quite recently. I'm going to skip over some of these things, but if there's a chance that this talk, the slides, could be made public, then whoever wants to get into the details can look at the references. Here, this is the reference list from this review paper that I just showed you. And continuing on, you can find some of the familiar papers here. And so let me start part one, quantum gravity. I keep asking people, what is quantum gravity? It's kind of a silly question to an audience of experts here. But I think there's it's something that's worth thinking or reconsidering. What I found over the last 30 years, or more, in fact, 40, there is something in agreement, that is quantum gravity theories refers to theories for the microscopic structure of space-time, okay? If you think this is otherwise, maybe in the question period we could delve into that further. It's a noble quest, it's the same noble quest, but the approaches and methods towards this lofty goal differ widely, which is why the different ways are quite well represented in this conference. Right? Now, the conventional approach started from the 50s of the last century, as practiced mostly in the general relativity community, is to quantize the metric or the connection form. All right? Now, this is the question I raised, and the reason why I haven't written one paper on quantum gravity. And that is, we know general relativity works very well in the description of the large-scale structure and dynamics of space-time. And metrics and connections are macroscopic variables, as far as we could tell. In fact, it works marvelously well for larger scales, cosmology. Why do you believe that quantizing these variables will reveal the microscopic structures? That was the question I was asking myself and everybody else for the longest time. Well, people usually say, look at EM field, gravity is similar to it. Yes. Helium-4, yes. But is this a universal paradigm? No. Universal meaning it applies to all cases. And the answer is no. Quantization of a collective variable does not lead to microstructure, okay? So what are collective variables? Well, there's abundance of examples in condensed matter physics which deals mainly with the dynamics of collective variables, of atomic interactions. So there they know what the microscopic structure is, the atoms, we all know. But they are more concerned with the collective degrees of freedom in its multifarious manifestations, like phonons, protons, plasmons, excitons. There are so many ON endings, right? So one can quantize sound, for example, and study the interaction of phonons with the electrons. That's the second chapter in any condensed matter textbook. Okay. So these ONs are all quantum entities, but does quantum imply microscopic? Certainly not. So a crucial question to ask, more important than quantization, at least for me, for the last 30, 40 years, is the following. Are metric and connection forms fundamental, depicting the microscopic constituents at the Planck scale, or are they collective variables constructed from them? The them we don't know yet, and that's what the noble quest I referred to earlier. So then the question becomes, is general relativity an effective theory valid only at large scales or low energies, like hydrodynamics with respect to molecular dynamics? And in this latter case, we know pretty well how to derive hydrodynamics from molecular dynamics via, conveniently, kinetic theory in between. So kinetic theory is kind of a mesoscopic theory with respect to molecular dynamics, the micro theory, and on the other hand, with respect to the macro theory, which is the hydrodynamics theory formed from it. All right, so this is the time to sort of make clear my own position, declaration. That was written in this essay in 1996. That's the second Sakharov conference. Because of Sakharov, I was bold enough to put forth this theme, this thesis. And it was developed a little bit later in 2005. But actually before that already, there are two essays that I try to sort of shift people's viewpoint a little bit, like cosmology as condensed metaphysics. And there's a long story behind all of this because at least in the 60s and 70s when we were educated, cosmology belongs firmly to the noble side, which is high energy physics, particle physics, general relativity, and all that. Condensed metaphysics, people say, all right, that's easy. We know E&M, everything comes out from it. It's only later that I learned that that's certainly not true. Okay, there's a lot, and maybe in fact in cosmology we need some conception that apply to condensed metaphysics. Okay, so in reference to quantum gravity, general relativity is of the nature of a hydrodynamic theory, valid only in the long wavelength, low energy limit of some microscopic theories at the Planck scale. So in this perspective, geometry and in particular the manifold structure, even manifold. For example, yesterday's talk, Calabi-Yau, what is it? Kähler manifold. So my question is, if you have a pet theory about the microscopic constituents of space-time, that you firmly believe in it, I hope the first thing you can show us is where the manifold structure, the smooth structure, comes from. Okay, and that actually is a question that's not so easily sort of negotiate around. When you, for example, if you go to a talk, say, string cosmology, and then the first line is some string, and then the second line is the Friedmann-Robson-Walker space-time. I would say, where does that space-time come from? If you could show me through your string interactions where that space-time comes from, I would be much happier. Pay attention to that. Nothing wrong with it, but that's similar to the case of electron-phonon interaction. Okay, they have not quite addressed the issue head-on. Okay, so in this viewpoint, space-time is an emergent entity. So are its symmetries. Many of the symmetries that we're familiar with, that we impose as necessary conditions, they could be emergent also. Okay. All right, so the other people, who I should mention Volovic and Xiaogang Wen, and certainly my colleague Ted Jacobson, whose sort of thermodynamic approach is probably better known. So let's push on. The alternative, and this is, of course, what this conference offers a lot to, right, is the posit. You say, this is the microscopic variable. If you don't believe it, I'm going to show you, okay? The first thing I would like whoever says that to show is where does the manifold structure come from, or at least show us how it could be, derived from whatever these basic constituents, strings, loops, groups, sets, simplices, asymptotic safety, and so on. And I just want to emphasize there's so much work done in this by some of the best people in all directions. And in my proposing my viewpoint, in no sense do I belittle that. You see that actually we need both sides as physics progress. The progress of physics showed us we need to make some assumptions about what's there, the fundamental structure, the basic constituents. Not like in the 60s, someone crazy enough to say, well, they're quarks. Of course, that someone is Gell-Mann, right? And then you have to work out, right? The quark, the flavor, dynamics, and so on. All right, at least some of the hadrons match what the scheme is. And I think, I hope this is what my colleagues in these various approaches are striving for. Okay, so the question is, does your favorite theory depend on some background geometry? And if so, where does it come from, for example? All right, so this is a slide. Some of you might have seen this maybe even 20 years ago, but I think it's still useful. What's plotted here, on this side is classical, the other side is quantum, and then going vertically, it is micro going down to macro. Right? So you can see general relativity is situated here. Is a classical theory which applies really well in the description of the large-scale structure of the universe, for example, right? And traditionally, one would think that, well, if I just quantize a classical variable, it would give me quantum, referring to the microscopic structure or the constituents of whatever theory that you're working with. In this case, space-time in particular, right? So I've listed some of these approaches there. So basically, the one question I was asking refers to, there's a drop-down list. I mean, now we work with computers. If you click here, there's a drop-down list, which is from micro to macro. And so if we think about our starting point, that is, does it make sense to just take a macroscopic variable to quantize it, and naturally it will give us micro? I have great doubts on it, simply because we have seen so many theories which are effective theories, hydrodynamics being one of it, right? And why is it that, how is it that if you just take any macroscopic variable and quantize it, and you'll get what you want, meaning quantum gravity, okay? So if you look at the drop-down list here, going from micro to macro, or rather, what we are faced with, the challenge is to go from macro, try to deduce what the microstructure is. And I would call that quantum gravity proper. Whereas if you assume that you know the basic constituents, you need to show how the macroscopic structure, like the manifold structure, emerges, okay? So actually I use this slide with the emergent word in it much earlier than emergent gravity became popular in a way. Because logically, this is what one needs to do. That is, from micro, showing the macro structure, and maybe at the end, the macros, the mesostructure, and then the macro structure. Now, if you look at it in the vertical direction, well, then there are a list of totally different issues that we need to confront, which is similar to what I mentioned, kinetic theory in between, between the molecular physics, dynamics, and hydrodynamics. And, and in a couple of slides, I would illustrate at least the way that I would go about trying to sort of unravel or try to understand a little bit about the mesoscopic structure. Another key word is coarse graining, as we all know. If you're given all the fine-grained information, like even the computer printout of the 10 to the 23 molecules in a mole of gas, it's totally useless to look at that printout. What is useless is to say, well, the room is too hot here, okay? Temperature, the concept of temperature. So you can see that collective variable actually functions very differently. And if you, for 1 second, think about general relativity as a collective variable, then many of the issues that would pop out for you to try to pursue this investigation further would be very different. And that's what led me to non-equilibrium quantum field theory, okay, by necessity, in fact. So this is the list of issues: coherence, correlations, fluctuations, and stochasticity, collectivity, variability, non-linearity, non-locality. They all would come out, would need to be dealt with sooner or later. All right, so a quick summary of so far, what's said so far. Besides quantum, the classical and added conceptual dimension need be included in our consideration from this different perspective, i.e. micro to macro. So this points to the necessity of first identifying the correct micro or meso variables before consideration of quantization. And if I don't have enough time, let me just tell you, there are two routes that, I don't know, 20, 30 years ago that I decided. One is fluctuation noise. It's basically garbage, okay? Whatever is left over, and you look into the garbage can to look for whatever meaningful messages in there. Well, like the detectors, they all do that. Very simple, right? As Sherlock Holmes would say. Certainly not very simple, because these are usually corrupted information, things that we usually consider as noise, not worthy of paying attention to, so on and so forth. Yesterday we heard about relevant versus irrelevant. So here is, of course, you have to define the observer. The observer, like us, live at very low energy scale. And so what is it that we could relate to yet contain some hint about what had happened earlier? Isn't this what cosmology is about? Okay. All right. The other is very important, is the role of topology, because it's more resistant to environmental decoherence. So the task of emergence versus quantum gravity. I would define top as energy top coming from the Planck scale down. I know this is almost the opposite of many other people's definition. And for emergent gravity, it is to understand, the task is to understand how the macroscopic structure of space-time emerges or evolves from unknown microscopic structures. Whereas quantum gravity is going bottom up from today's low energy up, how to induce or infer microstructures from macro phenomena. And I must emphasize that these are two complementary tasks. It's not like you can just go from bottom up without any sort of guidance from top down. And similarly, of course, it might be easier to identify the target for people working top down with micro to macro, because you know what the macro end result is. The challenge there is actually the emergence mechanism, which is totally non-trivial. If I have some time, I would show you a couple of slides, at least the difficulties that I could imagine we need to overcome. All right, let me go a little bit faster. Coarse graining, I mentioned. Of course, that case depends a lot on what you want to see coming out of it, right? Because different coarse graining measures apply to even the same set of fine grained data would give you very different macroscopic outcomes, okay? And this is something I wrote in 1993 in a conference. And at that time, people were talking about decoherence, like decoherent history, consistent history, environment-induced decoherence, and so on. And I was saying, well, all right, there's a lot of mathematics proposed very, very well. But then the physical outcome depends a lot on the coarse graining measure. And there are two criteria that needs to be checked out. One is the stability with respect to the repetition of the same coarse graining. So it starts to stabilize. And then if you vary the coarse graining measure, right, there's certain robustness, okay? And this is, I think, behind also what Gelman, Hartle, and later on Halliwell, Maroff referred to as the quasi-classical domain and so on. So there's a lot of this kind of thinking that one needs to incorporate when you come down from top the emerging gravity program, okay? So in fact, likely new physics would appear at successive levels of structure. Notice that there's not just one level of structure. I think we might encounter many. Just think about, let's say, something nuclear physics versus QCD. I remember 50 years ago, people in the corridor would say, well, we don't need nuclear theorists anymore. Okay, we have QCD. Is it really true? I mean, even the hadron forces is not so trivial to derive it from QCD, even if you're given a big computer to do the lattice computation and so on. So be mindful that new physics may appear as successive levels of structure, described by nested set of collective variables from micro to meso to macro structures. And well, in this process, you probably need to take into consideration the back reaction. And if that were the case, it would engender dissipative dynamics, and that's where quantum open system techniques needed. The reason why I venture into these corners, like non-equilibrium that Renata mentioned earlier, or quantum open system, was because of this, okay? It's not enough for me to just keep saying this. We just have to start doing something about it, yeah. All right, another thing is about RG, the Radboud group approach, which is, you can see great work done here, right, by Frank and Renata and Jan. Their group going on for decades, really. It's quite, really admirable. And if you take this viewpoint that there are successive layers of structure, beware that the RG running may not be as smooth throughout, as new levels of structure may appear with new collective variables describing new interactions. And coarse graining measures may need to be adjusted with the appearance of each new level of structure. And as I just said, dissipative dynamics from back reaction requires real-time non-equilibrium RG. Okay, just something in passing. Okay, so these are the things that micro theories would need to work on. And I would just go quickly, list out a few things. Most likely nonlinear, strongly interacting, strongly correlated systems. Non-locality property, non-local properties can emerge. It's very involved, right? And in fact, one thing worth noticing is that micro locality is very different from macro locality. And even at different levels of structure, the sense, the meaning of locality could change very differently, meaning that if you are at a different level of structure, looking at the sub-level or the super level, it would appear to be non-local. So don't be surprised to see this, and we just have to face it squarely. So my attitude is take this equivalence, inequivalence of micro and macro locality seriously, because there's new physics to be uncovered. Excuse me. So our conception and the construct of the macro world may bear little resemblance to the micro world, okay? As I just said, locality at one level may have little to do with the locality at other levels. And so let me just quickly say something about bottom-up, because that's what I think is something possible. And I think that's the way that physics has progressed over the centuries, because this is something that our experimental colleagues are very eager to know. Okay, show me how can I find out whether your theorem or thesis are actually realistic, meaning something that they could check out. Okay, I've said this already, and here's one hope. When I look at this micro to macro, there are actually parallels. Okay, for example, we talk about magneto hydrodynamics, and then in QCD we have magneto-chromo hydrodynamics. So the overall structure is quite similar, even though, of course, QCD and QED are quite different at the microscopic scale. So there's some hope that maybe we could have some geometrical hydrodynamics similar, with a similar behavior as some of these better-known theories. And as I just mentioned earlier, topological structures, because they are more resilient to evolutionary or environmental changes. And we've seen many excellent work on topological features in manifolds. And also, at the same time, in the last 10 years, there's a lot of progress in condensed matter physics of tensor network. And yesterday, there was a talk about tensor network field, tensor field. I think that's certainly an improvement. And we could also see string nets or bin foam and so on. So those are all very important features. And noise and fluctuations, which is something that I focus on in my research, my own research. So let's get down to the main topic. If we rely on noise and fluctuations, I will give you examples, the three that I mentioned earlier, that you actually need to. It's not sort of free to do so. And there is such a theory called semi-classical stochastic gravity. The main advantage is that it minimizes speculative assumptions. There's no room for any speculation because it's based on quantum field theory and general relativity, right? And it's a natural extension of well-known and tested theories, quantum field theory in curved space-time, semi-classical gravity. So this is the main theme of part 2 and 3 of this talk, which is quantum fluctuations. And the two topics, gravitational decoherence and gravitational entanglement, I think I would have some time to cover. And then the third part is graviton noise, okay? And the theoretical basis for low energy quantum gravity and quantum information phenomena would be the stochastic semi-classical gravity. All right, so this is sort of going back, and a lot of these development came from the mid-90s. Certainly quantum information took off around those times. And this slide basically compares the area that stochastic gravity started about 94 or so, had been applied to mostly strong field conditions like the early universe or the late stages of black hole collapse. And, but interestingly, there's also things going on since the 60s for people focusing on quantum mechanics and trying to change quantum mechanics to explain, for example, the collapse of the wave function, things like that. And this is just to warn people that the semi-classical gravity defined here is very different from the semi-classical gravity, the terminology used in this community. That's all, okay? All right, so what are they? So these issues, how does environmental effects affect the quantum coherence of the system, right? And how an entangled state evolves under the influence of its environment. So this certainly gets into the emergent field of relativistic quantum information, where relativistic refers to either special or general relativity. Even simple things like time dilation play some role when we look at quantum information issues in this relativistic context, okay? And the gravitational decoherence that I refer to is specifically by noises of gravitational origin, okay? And the gravitational cat state comes from the entangling between two masses, a topic I mentioned earlier that's caught a lot of attention recently, okay? All right, so let's get on to it. And if you are interested in some of the references of gravitational decoherence, you can see it here. And I just want to point out that already there have been gravitational decoherence theories or theories like that, like the DOC Penrose, even though Penrose never wanted to use the word decoherence, and Garadi, Rimini, Weber, and Pearl and Bassi, the continuous collapse, okay? I want to mention this because you'll see in a moment that if you adhere to general relativity and quantum field theory, even though taking the weak field limit and the non-relativistic limit, you will get something totally different from what the alternative quantum theorists would like to see, actually. All right? So a second point is that the noise is from the weak gravitational perturbations of Minkowski space. So these are the only dynamical or propagating degrees of freedom, and they are the gravitons, okay? Not the Newtonian force. All right, so what we found is that, let me just skip this and give you the first equation in the talk, which of course this is the Einstein-Hilbert action, and then this is this massive scalar field as an example. And you'll see the mass equation is Markovian in nature. This is the simple Liouvillean form, and this is just a tensor projection operator on pi. These are the momentum, right? So if you combine them all together, you get simply just p squared here. So the decoherence is actually in the energy basis, p squared over 2m. In the non-relativistic case, of course, is the energy. It's not in the configuration space basis as the alternative quantum theorists would like to see. And the reason they want to see that is simply, well, we know that below a certain scale, the system behaves quantum mechanically, right? But then above a certain scale, it behaves classically. So let's find that scale. So if you want decoherence to work for this purpose, you say that it decoheres at that scale. And then here we came along and did some calculation, we referring to Anastopoulos and also Miles Blanco. Obviously, for someone who understands general relativity, it's the energy that mediates the interaction. So this is the first point. The second thing to pay attention to is this capital theta parameter. There are two alternatives. If you go by the Minkowski spacetime as the lowest energy microstate, then that's a Planck scale, and you can see that there's just no chance. You can see that this is a big number, and the decoherence time is really short, right? And however, if you think that what we see today is a macro state of the collective variables, okay? Well then, you can set this theta to be much lower, and hence a greater chance for you to see gravitational decoherence effect. So if you're an optimist, if someday, well, it takes a lot of work because you need to isolate the other influencing factors, primarily from electromagnetic forces, of course, right? And if one day you can come close to identifying that this is indeed a gravitational decoherence effect, Then maybe you can turn this around and use the decoherence time to infer whether gravity is fundamental, meaning at the Planck scale and all that, the quantum effect shows up in the Planck scale, or emergent. So what we used, of course, was the sort of ubiquitous model, the quantum Brownian motion. So if you think for a second about quantum Brownian motion acting as an environment to decohere a quantum system, there are at least two parameters. One is the temperature, obviously. The other one is the spectral density. So what is the spectral density? It's kind of a mesoscopic structure for different collection of harmonic oscillators. You can actually design different spectral density functions for your different environments. And here, this theta is characteristic of the spectral density of what environment? The graviton environment. So I coined this word, the texture of space-time. It's not quite the micro, but at least it's something reflective of the collective action of the environment on the system. So if you're an optimist, one day gravitational decoherence may also reveal the textures of space-time. All right, so let me get to gravitational cat state and another list of references. So let's start from something really simple. If you want to construct a gravitational cat state, let's say one mass located at minus x, the other one at plus x, okay? Right away, you know that semi-classical gravity doesn't work. It's not sufficient for quantum information since it gives the mean value of the stress energy tensor, T mu nu. So you will wrongly conclude that it's right there, it's always there, well, which defeats the whole purpose of an entangled state, right? There's no superposition, no quantum, all right? So quickly, here's the semi-classical Einstein equation, the classical stress energy tensor, and the quantum one. And let's say you pick your favorite scalar or quantum field, let's say massive scalar field in this case, and you have to solve these two equations self-consistently, right? So notice this is the expectation value, right, of a stress energy tensor operator. So, well, if semi-classical theory can cope, it does not emit cat states, so the quantum information in the face of gravity really needs to go beyond, okay? So we must include contributions from the fluctuations in quantum matter field in addition to the mean. Fluctuations is just another way to express correlation. So really the important quantity at this level of understanding would be the correlations of the stress energy tensor. They are needed to address issues in quantum information with gravity. And there's such a theory, as I just mentioned earlier. And let's take a look. So here we have an S. And so the stochastic term appears here. Now, of course, it's not so easy, just write down a term in an equation there. You have to make sure that, first of all, an Einstein equation and all that, the marble palace and all that, could never allow any stochastic thing intruding, okay, intrusion. And that took me some years to think through. What turns out to be the case, of course, the fluctuation is really just another form of the two-point function of stress energy tensor. That's what enters in there. And if you look at just the Einstein-Langevin equation, because now you have a stochastic term there, with the simple case of a perturbed, weakly perturbed H mu nu, you would, in general, see non-local dissipation and colored noise. This is what I referred to just moments ago. Okay, we're dealing with a quantum open system. And the two-point function actually is very well behaved thanks to its well-behaved properties for the stress energy tensor. It's symmetric, traceless, and divergence-free, traceless for conformal fields. So everything is fine. You just have to work a little bit harder with the bitensor in this case, and that the expectation value of the bitensor is called the noise kernel. So this is really what characterizes the next level up from semi-classical gravity. And it is at this level that we could start investigating quantum information issues like the cat state. Let me just flip through this quickly. Thank you. Yeah. So here at L over 2 minus L over 2, and then L plus L over 2, this is how you form the gravitational cat. And let's say you stick a classical probe there, and you can work this out. It's a very simple calculation. And I just want to highlight the most relevant part. Well, if you start with a many-body wave function, psi star psi, right? That, of course, is the number operator. And when you look at this more carefully, you see that, I'm skipping all over here, the mu here is actually the mass density, right, operator. And we want a two-point function of it. What is it? This is really the 0, component of the T mu nu T rho sigma that I was referring to, T mu nu x T rho sigma x prime. In the simplest form here, you can see it already creeping up, showing up in this simplest gravitational cat state situation. Right? So this is just to show you the noise kernel is nothing crazy or nothing sort of ad hoc. It is a two-point function of your stress energy tensor. And in the simplest case of non-relativistic weak field limit, it's your mass density operator. Okay. Now, if you put in a quantum probe, well, you'll get Rabi oscillation. So this is something people in quantum optics know very well, albeit here we're using gravitational force for the cat state, right? So the bigger picture, I could show it at the end, okay? All right, so let's move on to the third part, graviton noise. And the effect of graviton noise on geodesic separation. Of course, we need separation for anything gravity. It sort of started when Molik and Frank Wilczek wrote that paper. They basically actually follow what I developed since the 90s. It's kind of rigorous way of dealing with noise in the framework of Stringer-Keldysh, closed time path in or Feynman-Vernon, and so on and so forth. So it's okay, all right? And there are 2 or 3 other papers. The one that I'm going to tell you is the work done a couple of years ago with Professor Cho of Taiwan. Fine, okay. Let me skip over this and just show you very quickly, maybe in 2 minutes, okay, fast track influence functional. Again, starting with a harmonic oscillator, your system, one harmonic oscillator interacting with n harmonic oscillators bilinearly, because we could solve this exactly. And I usually want to try out something wherein we could find exact solutions before I check on everybody else's result and find out where exactly some approximations were introduced, okay, to see the physical viability of whatever conclusion being drawn, okay. So if you group all the environmental variables together, you can form this influence functional. So it's just, you can see all the Q variables are all now functionally integrated. And this is the closed time path integration. And this is known as the influence action. So everything is proportional to x now. The reason why you see x plus and minus, if you think the Stringer-Keldysh or the closed time pathway, one is forward in time, one is backward in time. But usually when I teach non-equilibrium quantum field theory, I would introduce the Feynman-Vernon because it's easier to see, for example, when you construct a density matrix, you take 2 wave functions and do it, construct an operator. What does that show? You have an x and x prime immediately. And then because it's the brass and cat is a cat, going forming an operator, you can see that one is progressing forward in time, the other is backward in time. So, thank you, yeah. Right, so without further ado, so if you do it this way, you'll have a 2x2 green function with all the favorite things in there. But noticeably, it is not the Feynman propagator, as we often does in the in-out formulation. And if you put in here, you can identify these two terms. Delta is the difference, sigma is the sum of the S and S prime in this case. And sandwiched in between there, the delta and the delta is the nu. And it's here that Feynman-Vernon introduced a Gaussian identity whereby you can introduce a probability distribution P of C and a new function, the C, the noise term. So this is all identical. There's nothing put in by hand. And it's only after that that I got, I was more happier to actually adopt a stochastic interpretation of this theory. So with that, you have the Langevin equation, and the variation of the influence action gives you the Langevin equation, which is, of course, something quite familiar, except, of course, all these are now non-local kernels. So moving forward to the case of graviton noise acting on geodesic separations. Let me skip this. I'm just showing in these 3 slides. There are 3 different cases, and they are quite similar in nature. And so let's go straight to the graviton action right there, right? And then the normal coordinates set up along the geodesic of the first mass. We define the origin of that on one mass, and the other mass, of course, we have this geodesic separation. And you can see that under these sort of low energy, non-relativistic conditions, it's really the Riemann tensor, 0i, j0, and so on. So let me show you the result. You do the same thing like the quantum Brownian motion example I gave you. And then you see the dissipation and the noise kernel, right, between the two difference variables. And it looks a little bit complicated tensors, but it serves the same function. And here's the noise kernel, right? So that's the noise term, which you will see. This is the stochastic effective action after you've introduced the noise. And then taking the variation, you see the Langevin equation in the same form as what I show you for quantum Brownian motion. So what we did after setting up the initial conditions, we try out, so this is the geodesic separation correlation given mainly driven by the noise kernel. And then we try out 3 different vacua. Minkowski vacuum, no surprise, the effect is minuscule, really small. High temperature, yes, you can get a little bit improvement, but usually high temperature is difficult to identify this gravitational aspect anyway. And finally, the squeeze state, there's some hope because you can propose whatever. The universe had undergone tremendous expansion, inflation, and you get a large enough squeeze parameter here to magnify the effect. And so that's basically what we've done. Conclusion, for this last part, the quantum effect of graviton can manifest as noise on the detector. The vacuum, the effect is too small. Same for thermal state, but for the squeeze state, there is a possibility in detecting the primordial gravitons from the inflationary era. And finally, the summary for this whole talk, or the second part of it, quantum fluctuations in gravity, noise enters in decoherence processes, correlations enters in entanglement processes, and graviton noise effect on geodesic deviations. And stochastic semi-classical gravity is a reliable theoretical basis for low energy quantum gravity and quantum information phenomena. Thank you.
Yes, thank you very much for reminding us about the really difficult questions, and we were treated to, 3 for the price of 1, I guess, in terms of information density. Can I invite questions from the audience?
Yes, I was caught by your statement that we first have to identify the microscopic variables and then go through the quantization procedure. So is there any way to bypass knowing the right variables without doing quantization?
I heard only part of that. So you're saying that can we bypass identifying the micro variable, and
is there any chance that we know beforehand that these are the right variables before going through the program of quantization and showing that it works?
If you think about high energy physics in the 50s, not the 60s, okay, before quark came into our consciousness, what have people been doing, right? Proton-proton scattering, all the things that we could do. And as I said, we really need help from both sides, people working very hard to find contradictions. And on that point, I've been telling younger people, don't rush into Q cross G. It's very difficult. Of course, there are still many successful cases. But even with Q plus G, because of the intrinsic contradictions between quantum and gravity, there's a lot of things that we could think about, right? So it's similar to in the late 50s, early 60s in particle physics, what people were thinking about, the anomalies and strange behavior and so on. On the other hand, there's this genius, self-proclaimed genius at least, which is true, Gell-Mann, I said the eightfold way, okay? And he started working out, and that seems to match some of the resonances that they detected. I think it's a painstaking road, but physics has always been going on like that, right? From atomic physics to nuclear physics to particle physics, yeah. Daniel, is that? Yeah.
Hi,
Yes, for intercepted. Good.
Intercepted microphone. Go ahead.
So yeah, thanks, Bella, for this talk. And I agree with you that like this quantum fluctuation, this quadratic quantum fluctuation is really a key that we need to look more into in quantum gravity. Now, it sounds like a technical question, but I'm a bit surprised by one aspect that doesn't seem to appear in your derivation, which is that, my little experience with this 2-point fluctuation of the energy momentum tensor, especially at coincident point, is that it's rigged with UV divergences.
Can you speak a little bit slower?
Yeah. So it's the problem of the problem with this, or one issue that I see with this 2-point function of the energy momentum tensor, and that's an opportunity for us, is that it is rigged with ultraviolet divergences, right? So this 2-point function is in fact infinite in usual quantum field theory.
No, they're actually they're finite, actually. They are, of course, distributions, but all the divergences are contained in the T mu nu. So if you have some way to regularize it, it's okay.
But but in some sense, that's what we need quantum gravity for. What we need quantum gravity for is to find a proper UV regularization of this 2-point function of the energy momentum tensor. And if I understand properly, the relationship of between the 2-point function and the 1-point function, defines the diffusion constant. So I would say this is somehow quantum gravity observable, the way that things is regularized. Anyway, what I want to say is that, naively, this object is not small, it's infinite, and therefore it gives us a leeway that it might be bigger than we naively expect.
Right. Well, in general, I could respond this way. I would look at this from the whole hierarchy of correlation functions, and this is just one step going from the expectation value of stress energy tensor to the 2-point function. Or you can also continue on with the endpoint function. already, as I said, the two-point function, there's no divergence if you regularize well enough the stress energy tensor. Yeah.
We'll have to chat about it.
Okay, one final question, Daniele.
So you said that the coherence scale for gravitational decoherence is not necessarily the Planck scale if you don't come from the quantum gravity and instead you take the point of view of emergent gravity. Do we have a theoretical estimate of what could be that scale?
Right, that capital theta factor, right? That, of course, depends a lot on what kind of emergent theory. And that in turn depends on what you start out with, like string spinets and so on and so forth. So one would expect, our colleagues working on those things at some point present, for example, the mesoscopic structure. And we could then compare it with the spectral density function of this, let's say, harmonic oscillator or whatever environment there is, and then see if we could narrow down to the range that's physically feasible. Yeah.
I think we'll have to move on. Keep all your good and hard questions for the next break for Bailaku, and let us thank him very much again for his talk.
Thank you.
While we get ready for the next talk, could people kindly move in, because there are people sitting on the stairs, standing behind there, so that everyone can get a seat. If everyone who is still seated would kindly move towards the middle a little bit to make space. This is my next session. And could also someone please close the doors behind there, because there is a lot of background noise coming in there. Okay, let's move on to the focus part of the first morning session. I'm very happy to welcome Hans Hepach, who is working on his doctoral thesis in Vienna at the Institute for Quantum Optics and Quantum Information. So he studied originally in Germany, so I gave you a little background, and then an Erasmus brought him to Vienna where he got stuck, is my understanding, working in the group of Markus Aspelmeier. And he's been crucially involved in experiments on tiny, tiny masses. So he's an experimentalist, and he's been, he takes a crucial role in preparing, in making these very, very ambitious experiments for smaller and smaller masses, and that's also what he's talking about today. And I'm also very grateful that at very short notice he's agreed to step in for Aspelmeier, who was originally planned to talk here, but I'm sure he'll fill his feet happily and very expertly. So thank you very much.
Thank you very much for the introduction. So I'm a PhD student with Markus Aspelmeier in Vienna. And so first off, I need to apologize on behalf of Markus that he couldn't be here. He really wanted to come, but in the end it didn't work out. So let me quickly start by saying what we are actually doing in Vienna in our group. So the main question, or the main focus of our work is designing and performing experiments at the interface between gravity and quantum mechanics. This part, or these questions are actually pretty old for our field, let's say, as these questions have already been discussed in the 50s. So I'd like to start off with these quote from John Wheeler, who said that it is the challenge of checking whether gravity actually extends to smaller and smaller masses cannot be evaded. This is a quote he made at the 1957 Chapel Hill Conference, where two of the most prominent questions that were discussed were, do gravitational waves actually exist? And on the other hand, do we need a quantum description of gravity? I think the first question, so whether gravitational waves actually exist, has been quite well answered now. But the question of, or the experimental verification that we actually need a quantum description of gravity is still outstanding. And this is where our focus lies. If we go on to answer this question, there are two possible approaches to the problem. One is, well, we can just assume that there exists some quantum theory of gravity and then just probe its low energy consequences. Or on the other hand, we can assume nothing about how this interplay actually works and just, well, probe the quantum configurations of gravitational source masses. There are two main differences between those two approaches. The first one is, if we assume that there exists a quantum theory of gravity, we don't necessarily need to actually measure gravity. So there's no need for actual gravity measurements, whereas in the second case, we actually do need to measure gravity. So in a sense, the second approach, although it doesn't assume anything on the theory part, it is much more challenging in terms of actually experiments, and it is the approach that we are focusing on currently. So we just heard a little bit about gravitational cat states, which is the overall goal of the experiments we are currently performing, although we are still quite far from actually doing those. But there are two possible, at least as far as we can see, there are two possible implementations of such an experiment. Both of them require large quantum states, but the difference is that in one hand side we have two large quantum systems or quantum states in the sense that their extension, their wave function is actually quite extended, and in the second possible way we have two superpositions which we want to couple gravitationally. In both cases, the entanglement rate between those systems is the same, and I just want to stress here that the generation of such an entanglement via gravity is obvious from a quantum perspective, but not so from the GR perspective. So why hasn't this experiment been done yet? The important part here is this entanglement rate, where we have where the mass enters of the systems we are looking at, the size of the quantum state, the decoherence time, and the distance between both partners here. So for the quantum experiments, the first part here is the challenging part, let's say. So you need to have this large quantum state extension, and the decoherence time also is crucial here. And from the gravity experiments, this d, the distance, the center of mass distance between both systems, is what is actually difficult to achieve. You need to keep in mind here that the center of mass distance can't be that small, because you also have to deal with the extension of your object, let's say. So in our case, where we performed gravity measurements of 2 millimeter gold spheres, obviously the center of mass distance can't be smaller than 2 millimeters, because otherwise you would be inside each other in terms of the masses. So another way of looking at this is to look at this plot here, where the coherence times of quantum systems is plotted against the mass of the objects. So we have the meta wave experiments where we have quite long coherence times, but the masses are pretty small. The optomechanical systems we are also working on in the group, they have larger masses but also smaller coherence times. And on the other hand, we have the gravity experiments where coherence times up to now don't play a role, but the masses are much larger than for the quantum systems. So the question here is, for the quantum side, how big can we make the quantum systems without losing the quantumness, let's say, of the experimental constituents? And on the gravity side, the question is, how small can we make the objects without, well, while still seeing a gravitational interaction between both masses? I've been working on the second one, so let me say a little bit more about the experiment we performed. The idea for the experiment is quite old now, so it is proposed in 2016. The main idea is to just take an object and modulate its position in space, and thus modulating the gravitational field it generates at the point of the source mass here. So, well, the proposal was for this kind of linear scheme. It kind of didn't work out, so we went further back in time and used a much older method of measuring here. So we decided on using a Cavendish-type rotational oscillator here, where we modulate the, we now have three masses. We have the source mass here, the test mass here, and, well, we need a counterbalance mass in order to keep the pendulum stable here. The advantages of such a system is that you are no longer susceptible to any translational motion that can occur by just walking by, or any kind of disturbance that occurs at larger distances than the separation of those two masses here. Yeah, so just a few key facts about the experiment. So the torsion pendulum consists of 2 millimeter gold spheres, which weigh about 80 or 90 milligrams. We have a rotational frequency of 3.6 millihertz, which means we have periods of 140, 160 seconds. The quality factor of our suspension is pretty low in this case, so a quality factor of 4 is nothing to brag about, but in our case it actually turned out to be a big advantage to performing the experiment here. The position of our source mass has been modulated by a couple of millimeters, so between 2 and 5 millimeters. Everything was performed at decent vacuum, 10 to the minus 6 millibar approximately, and at room temperature. So just to give you an idea of how this looks like actually in the lab, so we have our two masses here. We have a mirror underneath for detecting the rotational displacement of the pendulum itself. You can't see the suspension here because it's just too thin. And you also don't see the source mass because it's not in here. But you see the laser that is just shining on the mirror underneath the pendulum, and is going to be recorded on a position sensitive detector outside of the vacuum chamber. Now, the main goal of the experiment has been to show or to isolate gravity as the main interacting force between both spheres. But in order to do so, you need to make sure that, well, gravity is actually dominant in your system, which is the biggest challenge in these kinds of experiments. First off, you need to make sure that the direct coupling between the source mass and the test mass is actually well under control. In this case, the most annoying part is the electrostatic coupling, as well, electrostatic forces are much stronger than gravity. In order to do so, we needed to discharge our pendulum to well below 100,000 charges, which sounds like a lot, but if you take into account that these spheres are about 2 millimeter in diameter, 100,000 surplus charges is actually pretty low. Also, you have magnetic coupling between those two. This is a magnetic spectrum we took at the place of the experiment. You see quite strong 10 millihertz lines in the magnetic field, the reason for which will become clear in a couple of slides. But you don't see these in the pendulum response, which is how we conclude that magnetic coupling is not a problem in our case. Then we have the environmental disturbances, which means, well, everything we couldn't pin down. This is seismic noise, this is people walking by, this is, yeah, anything you can think of. And the only, let's say, fundamental noise source that we need to compete with is the thermal noise of the suspension of the pendulum, which is this black line in the spectrum here. So we are sitting on top of the thermal noise in the quietest parts of the day. Yeah, so let me quickly say a couple of words about the discharge. Discharging of the pendulum. We borrowed our technique from the LIGO discharge method for their suspension and for their mirrors. It consists of using nitrogen, which flows over a set of high voltage needles where we produce ionized nitrogen, so positively and negatively charged particles. We then measure the ion flow to make sure that we actually have both polarities in there, and rely in the last part on a diffusion process in the vacuum chamber itself to neutralize any surface charges that we have in the system. Even though we achieve quite low surplus charges on the test mass this way, we still need a shield between both masses, so between the test mass and the source mass, because even though we have only 100,000 charges, electrostatic coupling would still be about an order of magnitude stronger than gravity without such an electrostatic shield, which also limits the center of mass distance you can achieve, because you need to account for something solid in between there. So what do we actually see? So if we take a spectrum of our pendulum, we see that we have our modulation frequency here at 12.7 millihertz. It's a quite strong signal in the rotational displacement of the pendulum. And we even see the first harmonics of this, which comes from the nonlinear form of the gravitational potential there. However, such an analysis here is not the best way to make use of the data we have, because actually the environmental conditions vary by about a factor of 10 here. So this is the same data as on the left-hand side, but with shorter intervals. So this is just 1 hour chunks of data, and you see that the overall noise flow varies by a factor of 10. But if you do such a spectral analysis, you actually assume a steady state of your system, which is not the case here, obviously. So the reason for this varying noise flow here is that we are situated right in the city. So we have 2 tram lines that go right here, the blue lines. We have 2 ones going here, the green ones, and another 2, the red ones, and there is also a subway under construction right underneath the building. So obviously it's not the best way to perform such a precision experiment. And just to give you an impression of the annoyance of these factors, the gravitational field that is created by such a tram passing about 70 meters away from the experiment is on the same order of magnitude as the one we are actually measuring. So 70 meters sounds like a lot, but 90 tons is also quite a lot. Yeah. To further give you an impression how that actually manifests in the experimental data. So this is a seismogram. So this is not the actual data of our pendulum, but just the seismic movements around here. So first off, this is a timeline. So this is 1 hour chunks here, and the mean displacement of the size of the movement of the Earth. So first, what you notice is that well, it's much quieter in this part of the seismogram, which is just because it's during the night. Then, if you have a closer look here, where you see these little bumps here, they are quite regular, except for this one here. And this outlier here actually causes some problems because it delayed the identification of this noise, which is just the night bus passing by. Yeah, once we got that, we know that a spectral analysis of the data is not the perfect way to go about this. And to further stress this point, this is data of 1 weekend in the life of the experiment. So this is the well, already highly smoothed out version of the pendulum over the course of a weekend. So first off, we have these red periods where we actually performed work on the pendulum, on the table. So obviously the pendulum was excited there. Then during the night, you already see, well, it's quieter than during the day. That looks good. There is still something, well, this is you see also the difference between the weekday and the weekend before. There is something we don't know what it is. But you also see this kind of here. And this was the marathon, the Vienna City Marathon that was passing by, which is going just around the corner from the university. Yeah. So what did we do with the data we have? Instead of doing the spectral analysis, we actually performed the time domain analysis, because we have the continuous time separation of both masses, and we have the force that is acting on the pendulum. When we do this, we can extract a coupling strength between both as the single fitting parameter here. And if we do that over the course of the measurement runs here, which is 3 weeks, you see that, well, it's varying still quite a lot, but we can say, or let's say we can reproduce the co-data value for big G within the range of our systematic error here. So this is the co-data value here, and this is the value we get. If you compare that to the usual like plots you see from the co-data group, our value would be well somewhere there. So well outside any range, competing with the current best experiments in precision determination of big G. Yeah. So I just want to say that although we have identified these as systematics, we have not corrected for any of them, because that would have been too difficult in our case, and the only goal of this experiment was actually to show that gravitational interaction between such small masses can be isolated. So how do we go on from here? So there are two possible ways. One way would be to decrease the distance between both masses, and the other one would be to decrease the mass itself. I'm working on the decreasing the mass route. There's a second experiment being set up right now, which goes the distance route here. So just for size comparison, this is the current source and test mass, and this is going to be the source mass we are working on right now, which is on the order of a Planck mass. To do that, we moved the whole experiment to a mine, which is about 80 kilometers south of Vienna, where there's no subway and no trams and so on. And this is actually the best, or one of the best places to perform seismic and geomagnetic measurements in the world. So we are quite lucky to be able to move the experiment there. Now, to go on a little bit on the quantum side here, all those experiments I'm going to talk about right now are being performed in the group as well, and all of them merit their own talks. But just briefly, the main challenges from the quantum side is, well, that for the solid-state mechanical systems, they are large, which is good, but the coherence times is pretty small. On the other hand, you have the metawave interferometry, which have very good coherence times, but are limited in the size of the systems they can work with. And our goal is to use levitated optomechanics to, let's combine the advantages of both approaches. So one of those experiments is to measure the motion quantum ground state of a levitated nanoparticle, which has been done in our group in 2020 and before, where we achieved a ground state probability of better than 2/3. Another experiment which is going a similar route is to use a Kalman filter to control the system into the motional ground state, which we also achieved in this case. And the third route that we are currently setting up is to use levitated superconducting spheres to further increase the mass of our quantum systems, where we achieved pretty good preliminary results here in terms of the quality factor that we can achieve. So in essence, what we do is we have two approaches to tackle this question of designing an experiment for combining gravity and quantum mechanics. We have the bottom-up approach. Let's say bottom-up in this case means in terms of size, where we want to improve on the size of the systems where we can actually verify the quantumness of the systems we are working with. And on the other hand, we have this top-down approach where we want to show that gravity can be measured in the lab for very small objects here. So that's the group. Currently on the experiment for the gravity side, it's myself and Matthias who are working full-time on the experiment right now. For the Planck mass-sized object, we are pretty close to actually measuring something. So let's hope that in a year or two I can report back on those results. So thank you.
Yes, thank you for these fascinating insights into microgravity, or whichever way we might call it. Inviting questions, can we start with the online? Is there anything online? Questions that have come in? Yeah.
So there's one question on Zoom from Deepan Betal. He's asking, does cosmological expansion play a role in the coherence time?
The short answer is I don't know. Please keep in mind that I'm not, I really don't know much about the theoretical frameworks there. I'm more concerned with the experimental challenges, which are up to now big enough. Sorry.
There's another question. How do you characterize the quantumness?
For now, that's going to the motional ground state. So, yeah, being able to really show these correlations there.
So, Badri first had a question, and then.
You described the seismic noise in the system, and you described the moving of the experiment to a new site. Wondering, I missed the thing about seismic isolation. Would it not make some sense to, spend more time on the seismic isolation and try to improve the situation in Vienna? Is that feasible or not?
Yes and no. The problem with the seismic isolation in this case is that the frequencies we are dealing with are so low that the typical seismic isolation that you perform or that you do, for example, in LIGO, don't really apply there, because there the measurement band is above the isolation band, let's say, so you're relying on mechanical systems to be, well, far above their resonance, which means that if you want to measure something at millihertz frequencies, your resonance frequency of the suspension needs to be in the microhertz regime, which is very difficult to achieve. And also just keep in mind that for the quality factor of our system and the frequency we are dealing with, in order to measure or to really see the width of our peak in the spectrum, we would already need to measure for 3 months, and this is for millihertz frequencies. So for a suspension in the microhertz regime, that would be in terms of years, which is not feasible.
I had a double question. Thank you so much. A really nice talk. The first part was about why you did the experiment at room temperature and whether temperature control will add something. And then what sort of challenges you expect in the microgram version of the experiment.
So the challenge, let me start with the second question. The challenges in the microgram regime are pretty much the same as they have been before. The main part that permits us to perform these experiments in the microgram regime is the quality factor of our pendulum, which dramatically increased by just moving it. So this actually directly allows us to perform these measurements at the microgram regime. The first question about the temperature control is, well, yes, obviously we would benefit from performing these experiments at lower temperatures, but not as much as we would by optimizing other parts of the experiment. So temperature does play a role, but the scaling is just not worth the effort right now.
Okay, one final question over there.
Hi, I was wondering that in case of the Cavendish experiment, there was this screen that screens the different kind of interactions, but can it also screen the gravitational interaction somehow?
No.
Or at least modify it somehow, like,
Okay.
When you are moving it, it kind of dampens the effect that would go to the other side.
So the only way I can see how the shield actually influences the experiment itself would be if the shield itself is moving. So the important part here is to make the shield rigid and thus eliminate this possibility, which is, I think, what we succeeded in doing there.
Okay, well, thank you very much. Thank you very much to both speakers, by Locke and Hans, in this session. Before the applause, we reconvene at 11 o'clock sharp after the coffee. So thanks again. Can someone close the door up there, please? Thank you. Okay, welcome to the second session. Just a brief technical comment. We were reprimanded not to have anyone sit on the stairs under any circumstances because of fire regulations. So sit in your comfy blue chair, all of you, and enjoy the talk of our next speaker, John Joseph Carrasco, who's from Northwestern University. So he is very well known for his work on scattering amplitudes in relativistic quantum field theories and applications. He leads a group on A and I at Northwestern. So A and I is not what you're thinking it is. Well, A is amplitudes and I is for insights. And he will share some of those insights, I hope, in today's talk with us. So welcome and thank you.
Oh, thank you. It's absolutely spectacular to be here. This is a fantastic program, and it's awesome to see all these communities engaging. In my invitation to speak, I was asked to speak about double copy, but also share my opinion on important questions in which ways the field should go. And so I'll try to do that. I'll try to identify like questions that I'm particularly excited about throughout, but just to calibrate sort of where I'm coming from. I really do believe that data drives important physical questions, and I think gravitational wave astrophysics is becoming an increasingly important source for data regarding the classical limit of quantum gravity. And I think cosmology is an incredibly important source of questions involving the quantum evolution of space and time. And I really enjoyed both talks this morning. I think people taking seriously tabletop experiments towards novel insight is going to be increasingly exciting. So I'd like you to consider this talk more of an invitation than a particularly broad review for these topics. I think that the amplitudes field is growing, and application of what we're talking about outside of amplitudes is growing. There's a tremendous amount of work in classical solutions and gravitational wave astrophysics using these double copy ideas I'll be talking about. So this talk is going to be more of a, hopefully, an accessible invitation for people who aren't so familiar with these ideas, but I'm listing some reviews targeting different audiences for people who might get excited about this, and you'll be able to see these with slides that we post to the site. So I think if there was a theme to my gravitational related questions right now, if there was a theme to how I approach questions in quantum gravity, right now it's trying to identify what data-driven questions in gravitation can't be answered by asking questions of gauge theories. And I think if you can identify questions like that, then I think that's a way, at least for someone like me, to be learning a lot about gravity, because that's identifying something uniquely gravitational that's very distinct from other quantum effective field theories. Okay, so what's the framework we'll be playing with today? For the most part, it's going to be S-matrix driven. So the idea that we've got asymptotically flat space-time, and so we get to prepare well-defined states at past infinity, and then all the complicated stuff happens in some bulk, and then we get to measure well-defined states at future infinity. And the nice thing about a framework like this is this evolution is gauge invariant, or gravitational theories, linearized diffeomorphism invariant, which means that no matter how we started, how we got at this originally, we can reformulate the story we're telling We can try to find new patterns that make it easier to calculate the same quantities, that let us go beyond what we would do with other methods. We can try out ideas, and at the end, know whether we're actually, whether we're talking about the same thing, because we're talking about, gauge invariant quantities. And that's a very powerful constraint that lets us move pretty far. Our community Amplitudes talks to all sorts of communities. If you'd like to speak to us and you're not, please feel free to send me an email. I'm happy to speak to you. I think one of the things we do is we try to find questions that push what we can do easily, and the reason is that in order to advance, it's not just getting bigger computers. We actually need to find structure in the theories we're talking about that let us move on. I'll explain why sharply in a second, but one such question is, can any four-dimensional point-like quantum field theory of gravity be predictive to all orders and quantum corrections? Is there some sort of innate tension? And of course, we know that gravity and quantum mechanics are actually great friends as long as we regard gravity as an effective field theory, right? And this is as we heard earlier today. This is it's been formalized as effective. This way of thinking about science has been formalized in the language of effective field theory. But this is really how we always do science. We always do science talking about the things we care about in terms of the nouns and verbs relevant to the scale at hand. So if you're a surfer, if you want to go surfing, you're paying attention to how glassy the conditions are, not the properties of your whatever your molecules as they're interacting. And this is of course all over the place. Low energy. The right way of talking about the strong nuclear force involves exchanging pions, whereas at high energy we have full QCD. And for cosmological large-scale structure, a very efficient description is in terms of a very sticky fluid. And so a way of reframing this question, do all point-like quantum field theories of gravity, local quantum field theories of gravity, four-dimensional, do they have to be effective field theories, or can they remain predictive without some infinite tower of counterterms, losing locality? And we've got a candidate theory. This is this very, very symmetric theory of gravity, maximally supersymmetric theory of gravity. And it's got incredible UV behavior everywhere we look. In fact, through the fourth quantum correction, through four loops, it has the same ultraviolet behavior as the maximally supersymmetric gauge theory. And indeed, just pure gravity by itself, while divergent at two loops, displays surprising cancellations beyond what you would expect in pure power counting. So perhaps there's only a finite bit of help that's sufficient for good UV behavior. Could there be some sort of symmetry or structure to gravity that's maybe a little hard to find, scratching at the Einstein-Hilbert action? And one structure that we've discovered as we've been pushing these increasingly high loop order calculations is something that turns out to be very ubiquitous in quantum field theories. The structure of many of our favorite quantum field theories admits a double copy description. I'll talk about what that is. And this points to previously hidden structure, and it's generally yet to be understood at the level of action that we find it easiest to find when we're talking about sharp gauge invariant predictions, whether quantum mechanical like S matrix elements or even classical description of the solution motion. But one thing that's true is that this is already making it much easier to handle problems that we would have thought were intractable to calculate. And I want to just highlight many theories have this double copy structure. I'm just putting sort of cartoons as placeholders. So here, got our cartoon for pions, so chiral Lagrangian, the predictions for pions, Nebu-Golson bosons exhibit play in this double copy game. Here I'm showing a plot of alpha attractor models, of inflation, just nicely falling into observed, constrained realms of cosmological data. It turns out these models of inflation, the building blocks that go into these, coupled to supergravity theories, also have an incredibly nice double copy structure. QCD with massive fermions in the fundamental plays well with double copy, as does perturbative string theory can be described in terms of a field theoretic double copy, and I'll talk about how the type of constraints that go into finding the structure actually let you bootstrap up to string theories starting from field theories. So the advantage is that we can exploit this structure for simplicity and prediction, that by just tracking a small amount of information, there are algebraic relations that propagate it to the factorial complexity of the full solution. And so that's great. That means that there's a lot less moving parts when you're trying to do more and more complicated calculations. And that buys us a lot. It exposes beautiful geometry in the S matrix I'll give you a hint of. And it seems to be structure related to good UV behavior, as we're discovering more and more as we play with these theories. And it exposes a deep web of relationships between theories with just a very small number of building blocks. By combining them in different ways, you end up talking about predictions in a wide range of theories. Why do such generalized gauge choices exist? How can we exploit the benefits in all circumstances? I don't know the answer to these questions. This is driving a lot of the research of my friends and I. But we'll see how we're starting to get some answers the more we probe. Okay, so let me just motivate the section I'm calling the need for technical simplicity, or the perils of infinite employment prospects. So it's natural to ask, in these days of very, very large computers that can do all sorts of things, do Feynman rules represent a useful solution for going after some of these questions? After all, this is systematic, this is algorithmic, given some classical effective action, I can write down Feynman rules and just start drawing graphs and dressing the graphs, and surely there's enough computational power to get at the answers we want. But this is horrible for gauge theory, and it's out of its mind for general relativity, and the easiest starting place is just the off-shell 3-graviton vertex. And even if you're not interested in 10 loops in some gravity theory, but you just want to care about the perihelion shift of Mercury, perturbatively, right? You need the self-description of gravity, and the off-shell Feynman rule is 171 terms, right? Just for the 3-point. Now you series expand your Einstein-Hilbert action. You've got your 3-point term, your 4-point term, your 5-point term, and it's just a mess. So even if you're just tracking the cubic interactions, a single 3-loop diagram goes as 10 to the 20 terms. By the time we talk about 5-loop diagrams, it's 10 to the 31 terms. But the final expressions for your gauge invariant, your diffeomorphic, individual diagrams don't mean anything, right? It's only when you combine them to physical observables, or the root of physical observables like scattering amplitudes. Are you talking about something physical? Are you talking about something invariant? And those expressions, the final expressions, are quite tractable. The vast majority of the terms hanging around here is unphysical freedom, is gauge-dependent freedom that must cancel in your physical observables. And so, something like this, I said 10 to the 20 terms. When I add it up with all of its friends in n equals 8 supergravity, I get something that fits on a slide, right? This is just the tree level 4 graviton amplitude. This is some kinematics. And Yeah. So there's structure to be exposed, and one of the keys, one of the insights that really thrust the amplitudes field at the very beginning was the notion that we should be really calculating with on-shell physical quantities, and it contains all the information necessary to build all loop level amplitudes. And just to go back and look at our 3 graviton vertex but on shell, we see something pretty spectacular. Just for comparison, I'm comparing it with an on-shell gluon amplitude, right? So the above is the gluon amplitude. I've got some color weight, and I'll talk more about the color weight in a second. This is some structure constant in the gauge theory, and then some kinematics. And the physical graviton 3 vertex, you'll notice, is just the same as this gluon vertex, except I strip off this color and I replace it with another copy of the kinematics. I should say just something about these Lie algebra structure constants. We're not going to talk about being in any particular gauge group. All you'll have to keep in mind to get what's going on for the rest of the talk is that our structure constants are the adjoint representation. They're antisymmetric, and they obey Jacobi. And this Jacobi relationship that the structure constants obey can be seen as relationships between graphs that are related around a particular edge. And we'll see what that does for us in a second. So now that we're on shell, now that we're physical, and we've got Mathematica, are we ready to solve all our problems? Unfortunately, there's another complexity we have to grapple with here, and it's a complexity of insisting on local representations that make manifest the factorization on physical particles that we come to expect. And there's many reasons to insist on these representations, not the least of, if you actually care about getting numbers out, we know how to integrate stuff like this, whereas arbitrary integrals over all space and time are even more tricky. Well, so anyway, my whole point is this doesn't look so bad. I only have 2 distinct topologies, maybe a couple integrals to worry about. I go to 2 loops, same interactions. Why am I saying 5 points? Well, for example, let's say we want to talk about the radiation of the gravitational radiation of 2 massive bodies scattering or something. So here we're at 2 loops. By the time we get to 3 loops, we see that this growth isn't just linear or exponential, but in fact it's a factorial growth in distinct topologies that I need to consider with all relabels. And so I'm just plotting a nice log plot. So M at the bottom here is multiplicity at tree level, which serves as a nice surrogate for the number of graphs you have to worry about loop levels. You can sort of sew your tree together to make loops. And I'm just comparing the complexity of polynomial like graph isomorphism to exponential, like I've got theories with an infinite number of colors, so I only have to worry about planar diagrams, to sort of double factorial I have to worry about when I'm just considering cubic graphs. And so the reason I put this up here is because even if we have an exponential growth in our computer power, if we don't have ideas that let us tame this factorial complexity, it doesn't matter, right? At some point, you're going to saturate what you can do with available computers, and even to go to the next order, in loop order, additional multiplicity, we're out unless we have new ideas, new physical ideas, and this duality between color and kinematics I'm going to talk about represents a physical idea that's starting to tame this computational complexity. And to give you a feeling for what it's doing, I'm going to ask you to consider a villanelle. Does anybody, can I get a show of hands for people who know what a villanelle is? All right, I'm seeing no hands. Maybe people are shy. But so a villanelle is a very constrained poem. So here's a poem. I'm not going to ask you to read it. It's a fine poem, but we don't have time to read the poem. I just want you to notice a few features. All these lines are the same. All these lines are the same. All these words rhyme, and all these words rhyme. Okay? What's going on? There's some sort of minimal information going in, and then relations are propagating the information to a full solution with this villanelle, this constrained poem. So now I'd like you to consider the poetry present in this random representation of a scattering amplitude. This is the first representation we ever found for 3 loops, 2-to-2 scattering, for maximally supersymmetric supergravity. I've got supergravity on the right, and I've got the gauge theory on the left in the same order. I've stripped off the trees that encode the physical states, so we're just looking at the scalar weights then relative between the two. And so when I say there's a random representation, I'm saying we wrote the entire amplitude in terms of cubic graphs, in terms of cubic integrands, meaning, trivalent, 3 vertices. We all know, gauge theory has contact terms, and gravity certainly has, gauge theory has a 4-point contact term, gravity is a 4-point, a 5-point, a 6-point, infinite number of contact terms, but you can always assign these contact terms to a scaffolding of cubic graphs by multiplying, dividing by the propagator of the graph you're assigning it to. So you're just multiplying by 1, right? So it's fair. But there was no art to the assignation. It was just sort of it got the job done. It satisfied all the factorization channels, so we knew we weren't missing any information that could be hiding in Feynman rules. So the poetry I wanted to show is you'll notice that all these graphs are the same in the gauge theory, and their square appears in the gravity theory. All these graphs have the same dressing in the gauge theory, and the square appears in the double copy in the gravity theory. Now these have echoes of similar structures, sort of recycling these building blocks. But you can say there's a sort of rhyme, but there's not like an equivalence. All right, and as I said, this was just sort of a random representation of the gauge theory and a random representation of the gravity theory. But you see that these echoes of structure, you might, if you'd calculated this, start looking for why we're seeing this sort of structure coming back and forth. And what we found is something really spectacular and very constraining. In fact, it constrains all these diagrams to be given in terms of this guy. And once you write this guy the right way, then algebraic relations propagate it out for the gauge theory. And when you have that representation, it's literally graph by graph, the square of the gauge theory, the kinematic weights, keeping the propagator the same, the kinematic weights in the numerator squared, give you the gravity theory. And so what is this relationship? It's that color and kinematics, they dance together, they play well together. So I showed you that the color factors, they satisfy Jacobi identities, which means that the color weight of this graph is going to be the color weight of this graph plus the color weight of this graph. And you'll find these 3 graph relations around every internal edge, just relating the color weight. So in fact, the color basis of any given gauge theory amplitude is actually not minimal at all, and that's why you're allowed to have kinematic weights such that individual graphs aren't gauge invariant because they speak to each other across these different color weights. When you go to a minimal basis in color weights, then the kinematic sitting next to any given color basis element has to be gauge invariant. That collection of graphs that contributed has to be gauge invariant. Right? And we call those ordered amplitudes when you strip off the color after you're in a minimal basis. You've got some ordered amplitude, some partial amplitude. That's gauge invariant. In any case, it turns out you can find representations where the kinematics satisfy exactly the same properties, which means that you don't need to write down separately all the different graphs. You just need to find that basis graph and then propagate the information from that basis graph. And when you have it in this representation, what we found is that by stripping off the color weight and replacing with another kinematic weight, then you're getting predictions and related gravity theories. So again, the whole game is you establish on a scaffolding of cubic graphs, and you find kinematic weights that satisfy this relationship, the same relationships, the same algebraic relationships as the color weights. And when you do so, you found building blocks that you can combine to get different double copy theories. And if both theories are gauge theories, then your prediction you get here ends up being a gravitational theory. But it's not restricted to just Yang-Mills. For example, one of these kinematic weights could be pions in the nonlinear sigma model, in which case what you're generating are Born-Infeld amplitudes, or supersymmetrized to Dirac Born-Infeld amplitudes. So the scattering amplitudes of many relativistic theories admit a double copy numerator algebra. And so I've just got a list of theories here, and one reason I have this slide is so I can put the names of some of my favorite people on a slide, but just to organize things a little clearer, so some of our ingredients in generating predictions, full predictions in theories, involve color weights or higher derivative corrections, or just our normal friends or scalars, fermions, and vectors. And then by combining these in different ways, we get a wide spectrum of theories coming out. I think one thing that was exciting for me to realize is that predictions of open and closed and heterotic strings and superstrings, bosonic strings at tree level are linked to normal field theory scattering amplitudes by an effective scalar theory that's all orders in alpha prime. And so, the complicated stuff involving polarizations, yada, 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 are just in the normal field theories, we all know and love, like Yang-Mills. And everything that lifts it to being an open string is sitting as higher derivative corrections to a very simple bicolored scalar theory. And it turns out you can construct this scalar theory out of a very small number of building blocks. I'll say a little bit more about that in a second, but I want to get back to loops. The world is quantum. Wouldn't it be great to generalize to loop order corrections? So we asked Jacobi, and Jacobi tells us we should always generalize. And the generalization for loops is incredibly straightforward. Everything we were talking about holds at the integrand level. So, I've added a symmetry factor for, internal symmetries that show up in graphs. But again, we have this same relationship with color weights and kinematic weights when dressing gauge theory amplitudes. And if you can find such a representation, then a consequence of unitarity is that double copy structure will hold. That what you build via double copy will satisfy all factorization channels. Great. And so the consequence of this is that we can start doing calculations that we weren't able to do before. So this is 5.3 loops. This is the mess of graphs I showed earlier. It turns out the entire kinematic information can be encoded in just this one graph with algebraic relations propagating it to the rest. Similarly, for loops, the kinematic information can be just associated with this one graph and then propagated to the rest. And so instead of drowning in this sea of graphs, we can start focusing and learning and asking questions about the subset that encodes all the information. And we can even aspire to reframing our S-matrix questions in a way where these types of basis graphs play a fundamental role, obviating some of the bookkeeping involved with the sea of graphs that in our perturbative expansion are just demanded of us. And all sorts of structure appears. I want to take a second to talk a little bit about color dual model building. The traditional story with color kinematics is that color kinematics, the duality between color and kinematics encodes a linearized gauge invariance. You could start off with some, some theory of vectors where I'm allowing my coupling next to my 3-point, my coupling next to a 4-point to be distinct, right? So this isn't a gauge invariant story at all. But if I start calculating in a 4-point, I impose the duality between color and kinematics, that these guys are related, then I find that G2 has to be related to G1 squared. So I recover Yang-Mills, I recover gauge invariance by bootstrapping and imposing this algebraic relation. And this propagates through to a linearized diffeomorphism invariance in my gravity theory, right? So I've got this structure of cubic graphs and quartic, and when I combine them, what I end up is all the graphs that are necessary, including the 5-point contact. So this 5-point contact emerges from writing my Yang-Mills graphs in a way that's color dual, right? So double copy promotes linearized gauge invariance to linearized diffeomorphism invariance. This is a similar story in terms of a soft bootstrap. I could write down a scalar theory, a lightly derivatively coupled scalar theory with arbitrary coefficients. And when I impose the duality between color and kinematics, I recover nonlinear sigma model. I just recover pions. Okay, and so this is a standard story. I think the summary, though, is that for the theories we learned about color kinematics in, gauge theories, these nice effective, scalar theories, that the duality constrains outwards, right? So in multiplicity, in contact terms of multiplicity. But it turns out something fascinating happens when you allow mixed higher derivative contacts. So for example, if I just deform Yang-Mills with a trace F cubed term, so the simplest higher derivative contact I could give a gauge theory, and then I ask what happens when I impose color kinematics and consistent factorization. So I'm demanding that I'm building my gravitational predictions out of theories that are entirely color dual multiplicity. You get a remarkable constraint from the fact that I've got 3-point amplitudes at 2 different mass dimensions combining with higher derivative operators to talk about the same, to contribute to the same 5-point amplitude, and demanding consistent factorization. That 5-point amplitude rigidly locks the coefficients of all higher derivative corrections. I mean, with additional freedom of stuff that can continue to satisfy color kinematics. But for example, if you deform Yang-Mills with trace F cubed, you land on dF squared theory plus Yang-Mills. And this has spectacular consequences for trying to resolve anomalies in supergravity theories, like n equals 4 supergravity. The first divergence of a supersymmetric theory at 4 loops that diverges in 4 dimensions, the half maximal supergravity theory. And this is thought to be intimately related to an anomaly in this theory. And you can try to engage with this anomaly through double copying with a trace F cubed. But if you require a consistent theory, then you're bootstrapped to something that is no longer a local effective field theory. In fact, it requires an infinite number of counter terms. When you land on, when you double copy with this guy, is something that's called a twisted string amplitudes. These are string amplitudes where some of the non-locality has been removed, but not all. It's basically, but with additional higher derivative freedom that lands on open, enclosed, and heterotic strings. And so what we're seeing is unlike a lot of our bootstraps that effective field theory bootstraps that really know about the IR, something about imposing this type of structure starts placing demands on the types of things we can write in the ultraviolet. I promised I'd give you some exposure to some of the geometry that we see when we start looking at the S matrix in this way. There are two reasons I'm going to do this. One is because there's some pretty pictures we're going to see, but second, it's going to let me give a sense for how we really dive into some of these higher loop calculations when we're using this, for example, to probe the ultraviolet behavior of maximal supergravity at higher loops. So to set it up, so I've already sort of drawn this graph of graphs for 3 loops below. So got there are 3 cubic graphs that contribute at tree level, and you can think of having operators that just scramble connectivity around an edge to take you from one graph to another graph, or this graph to this graph. And a Jacobi is just represented by a triangle in this sort of graph of graphs. I mentioned that when I go into a minimal color basis, I get partial amplitudes or ordered amplitudes. There's one of these graph moves that preserves color ordering. And I called it a t-hat. And so one way you can get all the graphs that contribute to a gauge invariant subpiece or partial amplitude is by starting with one graph and then just applying t-hat to closure. And so what you get are graphs that have the same color order. And it turns out when you do this, you carve out the one skeleton of a polytope. It's called a Stashev polytope, also sometimes called dissociahedra. And this is true to any multiplicity. And so here are all the graphs that contribute to a 5-point amplitude. I haven't drawn them. Each node is one of those graphs that contributes to 5-point. There are 15 graphs. You might think you need m-2 factorial of these associahedra, one skeletons, to describe everything, because that's what you need to touch every graph once. And this is known as a Kleist-Coif basis, and it was proven sufficient by Del Duca, Dixon, and Moltoni some years ago. But you get additional constraints because of the duality between color and kinematics. It turns out you only need to know the boundary graphs, the graphs at the boundary of this volume of graphs, and then you've got Jacobi relations propagating information to the inside. So every edge on the outside is propagating information. It forms a triangle going to an inner nodes, and then Jacobis propagate those to the inside. So you actually only need to be specifying the boundary data, and then algebraic relations propagate that inside. That reduces the set of necessary ordered partial amplitudes, the associahedra, to m-3 factorial instead of m-2 factorial. That means there are relations between these gauge invariant amplitudes that you wouldn't, these gauge invariant quantities, these ordered amplitudes that you wouldn't necessarily expect. And this is because you can find representations where the graphs satisfy Jacobi. Great. And so this boundary structure you can get by starting with a half ladder with your fixed external legs and just applying U-hat to closure. So all of these guys can be chosen to be half ladders where the external legs are held fixed, and you're just permuting over the internal legs. This carves out a polytope known as a permutahedra. And you can invert these, so you can linearly solve between your sort of ordered amplitude picture or your graph-based picture based upon, depending upon what's convenient for you and what data you're starting with. Okay, so in the interest of time, I'm just going to zip forward a little bit, but all this holds true universally to all multiplicity for all of the theories I described in my in this sort of web of double copy theories. I think one point that's missed when you play these sort of boundary games is if you have a functional representation of what your half ladder should look like, that you only actually need one graph to any multiplicity. As long as you know how to talk about the half ladder to any multiplicity functionally in a way that satisfies these sort of kinematic Jacobi relations, then you get everything, right? Okay, but I want to briefly talk about how we can exploit this structure to extract predictions. And this question I want to answer is, given a generic representation, so somebody, maybe they use Feynman rules in the weirdest gauge, gives you integrands for theories in this web of theories. Can you still pick apart the physical content in a way that lets you recombine them in this double copy sense? So, for example, you've got a generic representation of a gauge amplitude, and all you want is a gravity amplitude. Is there a simple path forward? And the answer is absolutely yes. And it has to do with what was going on in this cubic scaffolding. It turns out, so remember, all of these triangles in the graph of graphs represents a Jacobi relationship that could be satisfied in a given representation, but doesn't need to generically be satisfied in a given representation. It turns out contact points, contact graphs in your double copy theory emerge generic. So if I satisfy Jacobi in my single copy theories and I double copy, then I go from a cubic representation to a cubic representation, full stop. And I've encoded all the information that I need. But if I'm violating Jacobis, it turns out I'm introducing errors in my representation that are proportional to contact terms in my double copy representation. And you can read off what the contact terms are as double copies of the violations of Jacobi. So I can just pay attention to, so I don't even need to find a representation where Jacobi is satisfying. I can take any random representation that I'm given, pay attention to any violations of Jacobi, and then double copy those to have contact graphs in my gravity theory. And I know that sounds abstract, but I'll show you how that comes together really simply. This is the full 3-loop example. So I'm starting with that random representation I wrote earlier, right? That this is the one that didn't satisfy any algebraic properties. It had some poetry with the gravitational amplitude, but certainly wasn't obvious how you could go directly from the gauge theory amplitude to the gravitational amplitude. Okay. Now, what we're going to do is we're going to assign the square to the cubic graphs for n equals 8 supergravity. This is just the starting point. This isn't the right answer. As I said, this is going to be missing information, right? Because I started from a representation that didn't obey the algebraic relations. Okay? But all the missing information is going to be associated with contact graphs, and I can read off what those answers should be. What I'll point out, though, is even this wrong answers satisfies all the cuts down to trivalent vertices, and it satisfies all the cuts down to all trivalent but one quartic. So all of these cuts are absolutely fine. And in fact, most of these cuts are fine. Only a few of these guys have missing information. So I need to add these 4 contact contributions, right? And then I'll have the full amplitude for n equals 8 supergravity. And I can just read off these contact contributions from what Jacobis are violated. And the results are really simple. And when I do that, I've got the full amplitude. This is entirely a valid representation of n equals 8 of this loop order. And I got it from an arbitrary representation of the gauge theory amplitude. Yeah, so here it is. Just to give you some additional examples that are a little more relevant to sort of current state of the art. This is how we built up 5 loops a couple of years ago. This guy, it's the kinematic weight in the gravity theory is quite verbose, right? Because I started from a representation that wasn't particularly beautiful. It didn't satisfy Jacobi. It was just a random 5-loop representation from n equals 4. But you can just read off what the gravity contribution is by the violation of Jacobis. Example, at higher points, it involves subtracting out some of the information we found at lower at lower points. But again, the point is you can just read it off from this, you know, so I really enjoy this sort of algebraic story between graphs, because it lets me know what I need to do deep in the heart of a calculation. But in some sense, there's something that's very gauge dependent about finding this choice that satisfies algebraic relations. And what's gratifying about this is that I don't need to find such a gauge choice. I can just use the information in whatever gauge I'm in a gauge invariant way to build a representation of my double copy theories. Yeah, and so this is actually letting us go very, very deep in some of our calculations. I don't have a lot of time left. I want to spend a few minutes just talking about some progress with classical solutions. I think it's very natural to ask, you know, given that you have this relationship to all multiplicity at tree level between Yang-Mills and gravity theories, you know, should we expect to see some sort of double copy structure in classical solutions to Einstein's equations versus solutions to gauge theory equations? And there's pioneering work by Donald O'Connell, Ricardo Monteiro, and Chris White began a program that said, you know, for exact solutions of Einstein's equations, the answer could be yes, at least for certain classes of solutions. And this has started a whole industry of people. And by no means is this an exhaustive list of references. You'll have to see some of the early reviews for this, but these are various ones that stood out for me. And the nice thing about this, you know, yes, these are particular solutions, but some of them are solutions that we get really excited about, like Schwarzschild and Kerr black holes. You can understand as double copies of gauge theory solutions in particular gauges, which let you start asking questions like about, you know, the emergence of the event horizon, the emergence of geodesics from these gauge theory solutions. And so there's been some very exciting work that's been happening recently there. You know, I'm going to remind you of some of the double copy positives, like why we want this is that constrained solutions means we can exploit the structure for facility and technical prediction. And there's a unifying web of relationships between theories that let us recycle information we make from predictions over here to predictions over there. And there's an open question about how far this can go. I think what we know for sure is that we can help out in the in-spiral regime, and it's very open questions about what we can do in terms of the merger and the ring down. I think, you know, there's and at least in the amplitudes community, Thibault famously in 2017, you know, it issued an invitation to our community to jump in and help out, and now the highest precision Postman-Kowski calculations in the conservative regime have been done with these sort of amplitudes methods, and of course, you know, this is being applied now to radiative effects. Is you could just using color and kinematics and like massive scalar QCD, you can bootstrap to loop level results for the integrand involving radiation. This has recently been integrated to make sharp one loop order corrections to radiation. Okay, so to close, many theories are field theoretic double copies, and we can systematically go deep, which means that there are tons of problems to explore and learn from. You know, most of this talk has been in the regime of scattering amplitudes, at the very end, I was starting to talk about classical solutions. I think there's a lot going on with the cosmological bootstrap program that is intimately playing with the nouns and verbs we're learning about in our exploration of scattering amplitudes in flat space-time, and there's starting to be an interplay between those communities. Yeah, and so I guess to close, I'd like to suggest that if you notice a twinkle in Albert's eyes, if you look closely, you might see Yang and Mills looking back at you.
Okay, thank you for a fascinating talk. Can I invite questions? Yeah, here. I don't know who was first. Okay.
So it's if maximal supergravity is a really double copy of n equal 4 Yang Mills, super Yang Mills, does it mean that it's finite because n equal 4 super Yang Mills is finite? And what happens with infinities in your case? Do you see infinities when you do these supergravity calculations? And what do you do with them?
That's a great question. So we do see infinities in the dimension that the theories are. So let me answer your first question first. The relationship between n equals 4 super Yang Mills and n equals 8 supergravity is at the level of the integrand, not at the level of the integral, right? So that means is if I've got a single derivative for Yang Mills, I've got double derivatives for the gravity theory. So I can still absolutely diverge faster than in the gravity theory than the gauge theory. And right now, we don't know where n equals 8 supergravity diverges. We know that through for loops, it diverged in the same critical dimension as the gauge theory, that there were cancellations such that it diverged at exactly the same dimension. But, now I'm talking about maximal supergravity, right? It's not n equals 8 when I go above 4. But what we found at 5 loops is that maximal supergravity diverged at a higher dimension than n equals 4. Sorry, at a higher dimension than n equals 4 super Yang Mills. So it's diverging faster, right? And so there is a chance that this could mean that n equals 8 diverges at 7 loops, like many people have predicted, or at 8 loops, like many people have predicted, but we won't know until we do the calculation. Right, and we're currently at 6 loops. That's what we're working on right now.
Okay. Up there.
Well, while we're waiting to get over there, you can say, well, why would you ever expect n equals 8 to be finite? Is there anything special about 4 loops that, or are you just doing all these calculations to lift weights or something? There are all sorts of all-loop order probes you can make that suggest cancellations beyond what we see now, but we don't have the full integrand yet, so we don't know.
Yes.
Thank you very much for the nice talk. I have a twofold question. So the first is, how much of that special structure carries over if you lose supersymmetry? And the second part is, you asked this question in the beginning, what parts of gravity can I not understand as a double copy? How far do you expect in the classical limit the nonlinear aspects of gravity to be represented in that double copy?
Great. So your first question, quickly.
Was losing supersymmetry.
Oh, losing. Oh, yes. No. So it plays very well with supersymmetry. So the structure plays very well with supersymmetry, but it's independent of supersymmetry altogether. Right? So we have examples of non-supersymmetric theories at loop level, including QCD and the fundamental massive fermions right? So not adjoint, not massless, not, not Majorana, so honest QCD at one loop level, satisfying color kinematics. And in fact, all these, some of these scalar effective field theories we don't know how to put in a supersymmetric context, but satisfy this duality between color and kinematics. These effective field theories that exist after integrating out vectors and such. And your second question was how much nonlinear structure do I expect to still see at the classical level for gravity?
Yes.
All of it, I mean, so in the sense that that if I can perturbatively solve Einstein's equations, then order by order in the coupling, I can express a solution in terms of perturbative gauge theory solutions that I've found a gauge where they satisfy the representation, the duality between color and kinematics. And not in terms of scattering amplitudes, in terms of the levels of equations of motion. This was spectacularly done through the 5-point order by Xiaoshen a few years ago. It involves modding out by what you'd mean by the scalar propagators and tracking the bookkeeping around that. But yeah, I absolutely believe it's encoded.
Okay, thanks.
Sorry, final rows. Yeah.
Thanks for the nice talk. I hear a rhyme in the story you're telling with the history of physics and Emmy Noether's work. She dismissed her PhD thesis as a jungle of equations. She was trying to understand invariant theory, and she was disappointed with the technique she was using. And part of her reaction was to Hilbert's Nullstellensatz, when Hilbert organized the whole ideal of generating a variety. And I'm curious about whether you gave us a lot of examples, and I'm curious to what degree you think the community has developed Hilbert's Nullstellensatz for this. That is, you're trying to organize a jungle of equations, a jungle of relations, and to what degree have you found the general structure underneath that?
Yeah, that's a great question. So I think in very special examples, well, so what would we consider a solution or something that would make us happier than a graphical operation that lets you jump between things in some on-shell prediction, but something that we could see at the level of the action, a kinematic algebra we can see at the level of the action. And so there are, I said generally it's not understood at the level of the action. That's true. We have examples where we can make this manifest. So self-dual Yang-Mills and self-dual gravity, I think, were the first where the algebra is completely under control and you can make manifest at the level of the action, I think. Nonlinear sigma model is also an example. So Clifford Chung and collaborators have a spectacular representation where they make the kinematic algebra manifest by introducing some auxiliary fields. Although I'd say that's not nearly as evocative as a self-dual story, and it feels it feels like there's definitely more to learn. So I think it's one of these cases where we've seen tantalizing structure. It's an old story, right? This notion of thinking of gravitons as gluons with some infinite, color weight, some infinite dimensional color weight sitting next to them. And so, gravitons as gluons with the kinematics of gluons as the structure constants. I mean, it's tantalizing. The fact that it's realized in a way that lets us progress in calculation has been driving a lot of this. And there is a lot of work with evolving success in trying to understand the right ways of talking about things in terms of Lagrangian densities or actions. And yeah, I wouldn't say there's a complete story there, though, and I think there are a lot of lessons to learn.
Thank you.
Yes, I'm afraid, since time is pressing, are there urgent online questions? Can you pick one of them? And
Okay, so is there a double copy understanding to the memory effect in GR?
Yes.
good, next question.
Is there a double copy solution to explain classical GR with quantum matter, for example, for quantum primordial fluctuations?
So are you asking, do we have a handle on quantum field theory on curved space-time? Is that?
I'm not asking anything.
I'll answer that question. So this is actually, so again, a lot of what I talked about was really in flat space of like actual scattering amplitudes. There's a whole community of people working on generalizing to work on non-trivial backgrounds in the gauge theory, non-trivial backgrounds in the gravity theory. To what degree our understanding of, even like ADS or de Sitter, but quasi de Sitter and against plane wave backgrounds and such, and there are many lessons we're learning. Some things generalize trivially, some things we're still trying to understand. And in fact, I think it's this stretching beyond flat space scattering amplitudes that I think is going to provide us with clues towards finding a more full story. In some ways, flat space scattering, while incredibly challenging as we go to high loop order, it's still a very protected regime. And so as we're getting beyond that, I think we're learning more and more.
Excellent. So thanks for the great questions, thanks for the great answers, and another applause for JJ. Okay, so our final speaker of the morning sessions will be Benjamin Knorr. Benjamin did his PhD in Jena and then had a postdoc here, which we remember well, then went to the Perimeter Institute and currently works at Nordita in Stockholm. So he is an expert really on functional renormalization group methods, specifically application to gravity. And he'll give us from that perspective, his view on scattering amplitudes and maybe a more non-perturbative realm of those and what one has learned in asymptotic safety so far.
Yeah, thank you very much, Renate, for this really kind introduction, and also thanks to all the organizers for having me here. It's really a very nice program. As Renate said, so I'm trying to give you a more non-perturbative view on scattering amplitudes, mostly from the perspective of asymptotic safety, but I think there are also some lessons or a blueprint for other approaches to quantum gravity. And I would like to start actually with a perspective on quantum gravity, because we are kind of all sitting in the same boat, right? We want to describe this elusive theory, and we have the same problem. We lack a smoking gun quantum gravity experiment. So having this situation, of course, sparks a lot of interesting ideas, big ideas, even bigger claims about quantum gravity. And we had this excellent talk by Bianca yesterday, giving us an overview of these different strands that are investigated. But now you can say, well, why should you trust my ideas? Why should I trust your ideas? So to phrase it as a provocative question, why should we trust any particular approach, right? It's all about big ideas at the moment. And I think this is a fair question eventually we all have to answer. And I would like to answer this question from my perspective by giving you a recipe for a falsifiable and predictive quantum gravity theory. Of course, we have to work out the details in practice, but at least this gives you the general idea, right? So it's a 3-step recipe, and I think the first step is, of course, fixing the theory. You have to define what are your symmetries, what do you want to describe. You want to describe gravity. You also want to describe matter in the end, the things that we observe in the universe. So it should at least include something like the standard model on the matter side. Now, once you have this theory, you've your base point, if you want, and from that theory, you should do computations. You should make predictions and confront these predictions both with theoretical constraints, but also, crucially, for experimental data where you can. And I'm stressing here that it's really the simultaneous aspect that is really crucial here. Because, of course, we all have some free parameters in our models that we can tune and twist, and it's somewhat straightforward to get 1 or 2 specific things right in a certain model, but getting all of them right, or as many as possible, that's the real problem, I think. So once you're at that level, you can say, okay, at least I'm consistent or not in contradiction with collider physics, with cosmological evolution, with all these things, gravitational waves. Then I can think, or I can say that I have some trust in your theory. And only then I would say we can tackle the really big questions, like black holes, singularities, what happened at the Big Bang. Because then we have some trust that the theory is actually related to nature. And now you're probably not surprised that my tool of choice going through this recipe are gravitational scattering amplitudes. So this gives you a short outline of my talk. I'll briefly remind you a little bit about asymptotic safety. We had some excellent talks yesterday in one of the parallel sessions about this topic, so I'll keep that short. And then move on to the main topic of gravity-mediated scattering amplitudes, mostly with an asymptotic safety, as I said, but also with a little bit broader perspective. And then end with a short summary. Good. Asymptotic safety. What is it about? In its kind of simplest setup, if you want, the hypothesis is that metric gravity, as we know and love it, plus potentially suitable matter, like the standard model, as I said, maybe some dark matter, can be actually formulated as a quantum field theory consistently, but the kind of price that you have to pay is that you have to use non-perturbative methods. And how you should think about this is, or how we typically think about this, is in terms of a renormalization group. So as a very simple example, think of a theory. You have a single coupling, which is dimensionless, and you look at its RG flow across some energies, like Q squared Q is a momentum scale, so this is energy. Now, you all know asymptotically free theories where the coupling goes to 0 at very high energies. And the only difference in asymptotic safety is that the coupling doesn't go to 0, but it goes to a finite value at very high energies. Now, more precisely, what are the conditions for a theory to be asymptotically safe? Well, essentially 2. The first condition is, as I just said, all the dimensionless versions of the couplings, more precisely the essential couplings, should approach such a finite value at high energies, and we call that a fixed point of the renormalization group. The second point is, of course, well, this is maybe just not enough because we want to have a predictive theory, right? It doesn't really help us a lot if all these couplings have to be fixed by experiment, because there are infinitely many of them. We do not want to have this situation. We want to have, let's say, 5 experiments, fix the 5 free parameters in our theory, and then predict all the rest from that. So this is, of course, also a crucial requirement for a sane theory. So this really sets the stage for the rest of the talk. As we know, at least at a fundamental level, perturbation theory for quantum gravity has its problems. You know, for example, the 2-loop counter term that we see, that's the first non-subtractable divergence in GR. We expect more and more to come at higher loop orders. But I think we should not give up on QFT yet. In this talk, I want to zoom in a little bit and test asymptotic safety, at least, well, give you a perspective on how we could test asymptotic safety by connecting it to both theoretical and experimental constraints, and as I said, via the path of gravitational scattering amplitudes. And the whole underlying basis of this, or if you want my language, will be that of the quantum effective action, which is really the quantum equivalent of the classic action. It includes all quantum corrections. And this allows me to more or less straightforwardly handle all loop, at least in spirit, all loop orders. So with that out of the way, let me proceed to the main topic of this talk, gravitational scattering amplitudes. And we have to start somewhere, of course, and the easiest non-trivial example is a 2-to-2 scattering process. And this is also what I will focus on in this talk. So we have a mediated diagram and a contact interaction. Once again, since I'm working now with the quantum effective action, all these vertices and propagators are fully dressed, so they include all quantum corrections. This means that these are really the only two diagrams that you have to compute. Of course, for this mediated diagram, you might have S, T, and U channels, depending on the process. What are some benefits of this approach? Well, of course, you probe, in the end, quantum gravity effects if you look at gravity-mediated scattering amplitudes. But other really nice benefits are that there's, of course, this direct link to observables, as we just heard in the previous talk. Also, as we just heard, these are independent of arbitrary choices like gauge fixing, which, for example, in RG flow is not. And to reiterate again, since we are using the effective action, tree-level diagrams are enough to discuss this. Good. What's the general strategy for working with this from this viewpoint? Well, you fix the process that you want to investigate, and then you have to kind of parameterize the effective action, or at least that part that is relevant for this given scattering event. So you sit down, you think a little bit about the content of your theory, and what can enter basically these two diagrams here, right? So you have to control the propagator, a 3-point interaction, and a 4-point interaction for this 2-to-2 scattering. The second step, of course, is, well, you need values for the couplings or the momentum dependence of these couplings, and you have to get it from somewhere. And the way that you would do this in asymptotic safety would be from the RG flow. But of course, if you have another method, lattice simulations, for example, you can substitute a step with that. And then, of course, you have these nice amplitudes. You get some, I don't know, 2-to-2 scattering amplitude. You can get cross-section from that. And then you have to ask the hard questions. Well, is it consistent with theoretical constraints, like unitarity bounds, causality bounds? And is it consistent or does not contradict experimental data? Disclaimers here. For now, I will not talk about external gravitons. This is just a really difficult to define object, what an on-share graviton is. You can, of course, discuss about that if you have any good ideas. And as in the previous talk, I will focus on the flat spacetime and just standard asymptotic states, so really standard QFT scattering amplitudes. Because once again, we have to start somewhere, and then we can build up from there. So, first step, parameterizing. And I want to be very explicit here. Let's take the simplest example of a scattering. It's scalar scattering, right? So I have two scalar fields, scalar field phi, scalar field chi, and I scatter them that two phi's go into two chi's, and I can do that either by gravitational interaction or by this contact term. So what do we have to specify to compute this amplitude? Well, we certainly need a graviton propagator here, once again fully dressed. We need a 2 scalar 1 graviton interaction, and we need this 2 phi 2 chi contact interaction. Good. how does that look like at the level of the action? This looks a bit scary, I guess, but I will try to guide you through it. The first line really gives you the graviton propagator in flat spacetime in full generality. So of course there's an Einstein term. I put the cosmological constant to 0 because we are working on a flat spacetime. And then there are these two form factors, or what we call form factors. Think of them as just generalizations of some momentum-dependent couplings to curved spacetime. They depend on well, the covariant Laplacian or the Lambertian, if you want. So you have these two terms, which are basically controlling the spin 2 propagator and the propagator of the conformal mode of the graviton. The second line is the action for, or part of the action for the scalar field phi. You have some generalized kinetic term, once again with a form factor. You can have a mass, for example, in there. And then you have these non-minimal interactions, two types, each with an own form factor, which now depends on 3 arguments, delta 1, 2, and 3, where the index indicates which field it acts on. So delta 1 acts on R here, delta 2 on the first phi, delta 3 on the second phi. You have a similar term with a Ricci tensor here. A very similar term to this, you also, of course, have for the field chi that I did not spell out here. And the final term is this contact interaction, which depends in total on 6 contractions of momenta, if you think of flat spacetime. And of course, I want to emphasize here that these form factors, or what is really in there is the full momentum dependence, is of course key in any of these investigations, because we are talking about scattering amplitudes, and we are interested in high energies in the end to check something like asymptotic safety or unitarity. That's where the meat is, if you want. And let me also point out that we wrote a form factor toolbox, so a toolbox to deal with these very complicated objects some years ago. Good. Let's go towards the amplitude. Let me start with this first diagram, the mediated diagram. Once again, well, 3 lines of formula, so it's maybe not so nice, but actually it's super easy if you look a little bit about, if you stare on it. So it really splits into 2 contributions, a spin 2 contribution and a spin 0 contribution. The spin 0 contribution comes from the conformal factor, and the spin 2 from the actual like TT graviton, if you want. And then these 2 contributions split into different factors, actually. You get vertex factors, which come really from the vertices. You can see that. There's one factor from the left vertex, one factor from the right vertex. Same thing here in the spin 0 sector. Then there's the scalar part of the graviton propagator, which carries the momentum dependence of that propagator. And then the last ingredient is such a contraction factor, which kind of gives you the angular dependence in the spin 2 sector. It just really tells you that this is the spin 2 contribution, nothing more. S, T, and U are just the standard Mandelstam variables. Let me point out here that this expression is gauge invariant. We explicitly calculated this in a gauged fixed manner, but all the gauge dependence drops out, as you can see. So you have to trust me here, of course, that it actually does. The second diagram, the contact term, well, it's pretty straightforward. It's just depending on this 4-point interaction evaluated on shell. So there's not so much that so many simplifications that you can expect here. Good. Of course, this is a very simple example, scalar scattering, but the same recipe can be followed for really any scattering event. So we did the same thing just last year for scalar photon scattering and also photon-photon scattering. We also wrote a book chapter recently, which is part of this handbook of quantum gravity, which is hopefully being published soon. What is still on the table are fermions and maybe also some Young-Mills. And of course, also building up on combined systems. As a side remark, there are some recent developments in the field of asymptotic safety that we are now able to treat essential couplings or distinguish essential from inessential couplings. Just to remind you, essential couplings are the combinations of couplings that actually appear in observables, because, of course, at the level of the path integral, you can do field redefinitions. Field redefinitions do not change observables. So this will really give us a better handle on these amplitudes, because you can choose certain field redefinitions which make your computations much easier. And as I said, there's a lot of progress right now happening. Good. Let's get into the more complicated step, the computing. Here I have to focus again on asymptotic safety, because that's where my experience lies in. There's been a lot of work in the last roughly 10 years on the graviton propagator, and there was also a really nice talk yesterday by Manuel Reichert on some aspects of this. I think what we can say by now is that there's no additional modes in asymptotic safety besides the massless graviton. The spin 0, so the conformal mode, behaves quite a bit different from the actual spin 2 sector. And as Manuel showed yesterday, there are first efforts to compute really in Lorentzian signature, because usually in asymptotic safety, we have to also compute like integrals, and this is typically done in Euclidean signature. Beyond propagators, it's really getting tricky. At the moment, we only have a very limited information on the momentum dependence. There are some works, but really I think there's a more concerted effort needed. And of course, in all of this, this really needs cutting-edge computer tensor algebra and numerics. So you kind of win that it's non-perturbative, but of course, there's no free lunch compared to loop expansions. So somewhere you have to sit down and do the hard computation. To maybe illustrate one or two computations, I would like to pick out this paper together with Mark, where we computed the momentum-dependent anomalous dimension of the graviton propagator and the corresponding Faddeev-Popov ghost. So you can see the eta tt is the spin 2 anomalous dimension, eta 0 is the anomalous dimension of the conformal mode, and eta ct and eta cl are the transverse and longitudinal parts of the Faddeev-Popov ghost. And you can see that, as I said, the spin 2 and 0 behave quite differently. The spin 0 goes to 0 at high energy, whereas the spin 2 stays at a finite value. You can also see that the two modes of the ghost behave roughly similar. The second highlight that I want to make here is this paper, which was presented by Manuel yesterday, on where they computed the spectral function of the graviton. Good. In the 5 minutes left, I would like to talk about the remaining step, confronting with theoretical and experimental constraints. Let me start with the experimental constraints. And unfortunately, right now, I cannot tell you a lot, at least at the level of the scattering amplitude, because we are just not there yet. What I can tell you is that there are some first insights directly from the RG flow. For example, you might know this prediction of the Higgs mass from about 15 years ago, or the post-diction of the top mass. On the theory side, unfortunately, once again, we are still in the process of getting something. This whole project, or this whole line of research, only started recently, so please stay tuned. But once again, what we could do so far is already promising. We could deliver a proof of principle that asymptotic safety can actually coexist with unitarity and causality. And that's quite non-trivial, because there's certain conditions that are a priori independent of each other, and you have to make sure that you can actually fulfill all of this. And it turns out that these form factors have enough enough freedom to cover all these conditions simultaneously. But what we also found was quite a bit surprising, that these unitarity and causality bounds kind of need specific relations between a priori unrelated couplings. And there are actually some indications that in asymptotic safety we find this, but unfortunately there's not enough time to talk about that. Good, so let me summarize. I hope that you agree that falsifiability is at the heart of natural science, and as a consequence, it should also be at the heart of quantum gravity research, at least as much as we can. In my opinion, scattering amplitudes are a very promising tool to probe quantum gravity because they span both the theory constraints and the experimental data. The ingredients of these scattering amplitudes can be computed ab initio, for example, with an RG flow in asymptotic safety, maybe from Monte Carlo data. So there's not really a need to guess if you have a well-defined theory as your starting point. And once again, from my perspective, I think in asymptotic safety, we have some encouraging progress. The fixed point that we see is a very stable result also once we look into the more involved computations with all this momentum dependence. And this also shows that we do have the technology to compute these correlation functions. So we're getting there, but of course there's no free lunch, so stay tuned. Thank you.
Yes, thank you very much. Before the almost free lunch, can I invite some questions? Yeah, over there.
Well, my question is perhaps a bit ingenious, but did you already try to calculate some loop corrections within this methodology?
Loop corrections, so at least one loop. What we are typically using is the functional renormalization group. So one loop exact equation, so one loop is built in. Of course, since we are talking about non-perturbative physics, we have to make approximations, and approximations are typically not along the loop order direction, but orthogonal to that. So at higher loop orders, there's not a one-to-one correspondence, typically.
We have one question on Zoom. Could there be off-shell gravitons emitted by Hawking radiation, and could their scatterings be analyzed?
Sorry, could you repeat that?
Could there be off-shell gravitons emitted by Hawking radiation, and could their scatterings be analyzed?
Well, I would say we can only measure on-shell physics in the end. At least in the scattering amplitudes, the external states are on-shell. So this is within this line of thinking what we can talk about.
Are there any further questions? Are there any further questions? Everyone's ready to go for lunch. So thanks again for the speakers of this morning. Thanks. And